Hi everyone, this is Matt Touchot with Intro Stats, and today we're looking at a problem from my book, Intro to Statistics for Community College Students. And this is problem number 32 from section 4D, as in dog, 4D, number 32. So let's look at the problem. So this is the section on goodness of fit tests. So this is, it looks like just like a goodness of fit test. So we basically have some data. The National Highway Traffic Safety Administration, NHTSA, publishes reports about motorcycle fatalities and helmet use. The following distribution shows the proportion of fatalities by location of injury for motorcycle accidents. So the NHTSA is indicating that about 57% of fatalities are multiple locations, 31% are from the head, 3% for neck, 6% from thorax, and 3% from abdomen or spine. So random sample data of 2,068 randomly selected fatality from motorcycle riders that were not wearing helmets. Use a 1% significance level to test the claim that the distribution does not match the proportion of NHTSA. So here's our fatalities based on broken up by the part of the body that was injured. And again, what we're trying to see is, does this data fit with the NHTSA percentage data, right? Does this data? So this is our observed counts, and this is going to be the null hypothesis right here. Okay, so let's take a look. What would the null hypothesis look like? So something like that, right? Null hypothesis, so P or pi for multiple locations, 0.57. Pi for P or pi for head injury would be 0.31. Neck would be 0.03. Thorax 0.06, abdomen, spine 0.03. At least one proportion is not equal, and that seems to be the claim, right? They want us to claim that this does not fit, the observed data is not fitting with what the NHTSA has said. So we had 5 groups. So again, remember the degrees of freedom is k minus 1, where k is the number of groups. 5 minus 1 is 4 degrees of freedom. All right, let's take a look at what they gave us a StatCato printout here, which is good. So we have our observed counts and our expected counts. These are very interesting to me, especially with this kind of data. We expected 1,178 fatalities from multiple locations. We got 1,036, so it's lower. For head injuries, we expected 641 fatalities. We got 864. Now that's quite a bit above. We expected 62 fatalities for neck. We only got 38. We expected 124 fatalities from thorax. We only got 83. We expected 62 fatalities from abdomen, spine. We only got 47. So really the big discrepancy here, you can see it here, the contribution to chi-squared is the biggest in this group, and this is the head injury. So this is probably notice the only one where the observed counts was way more than what we expected. There should have only been about 641 deaths, but we got 864 deaths. And again, it's the highest contribution to chi-squared. So that's where there's the biggest discrepancy. Okay, let's take a look at our test statistic down here. Our critical value was 13.27, so this is a right-tailed test. That's where the tail starts. So the test statistic needs to be bigger than 13.27 to be significant. Is it? Yeah, the test statistic is 121, so way over, way over. So it's definitely in the right tail. So that means our sample data significantly disagrees with the null hypothesis. It also means our observed counts are significantly different than our expected counts. Our p-value was 0, so if the null is true, there's a 0% probability of getting the null hypothesis or more extreme by sampling variability. Okay, so all our expected counts are bigger than 5. They did say this was random sample data, so this is going to pass all the assumptions for a goodness of fit test. All right, so let's see. Again, sum of the averages of the squares of the differences between the observed sample counts and the expected counts is 121. Test statistic did fall in the tail, so sample data significantly disagrees with the null hypothesis, and the observed counts are significantly different than the expected counts. Our p-value was 0. There's our p-value sentence. P-value was lower than our 1% significance level, so again, the sample data is unlikely to have occurred by sampling variability if the null was true. We rejected the null hypothesis, right? Low p-value, which means the claim that that the data sort of does not match the proportions given by the NHTSA, we're going to support that claim. So there is significant evidence to support the claim that the distribution of the sample data does not match the proportion given by the NHTSA. I would make a side mark that if you looked at the data, actually the one glaring one was the number of fatalities for head injuries was way more than we expected. Again, they said this came from motorcycle riders not wearing helmets. So this probably would give some evidence towards requiring motorcycle riders to wear helmets. We only expected to get 641 deaths based on the injuries, and yet we got 864. So again, seems like we motorcycle riders definitely need to wear their helmets. All right, so this was number 32 in section 4D. This is Matt Tuchot and Intro Stats.